So I'm actually going to talk about Feather, the file format. So I guess real quick preliminaries. My name is Bill, as Steven said. I'm a data scientist at Civis Analytics, and I am not a Feather contributor. I just think it's a really cool project. So I guess quickly before we get started, who here works with CSV files? Okay, who has to share code with other people or share data with other people? And who does this with CSV files? What about Parquet or Avro or anything from the Apache Foundation? Okay, so a few people. So real quick, Feather is just a file format put together by McKinney and Hadley Wickham, based loosely on Avro, with the explicit intent of having essentially a cross-platform, cross-language way of exchanging data that maintains type information, metadata, and stuff like that. So CSVs are obviously not typed; they're just text. So you lose a lot of information, that kind of matters to a lot of stuff that we do. So there are no date-time types. There are no categorical types. You essentially get strings and numbers, and it's up to every CSV parser implementation to sort of decide how to interpret those things. So one of the ways that Feather improves on this is, again, it records the type information when the file is written. So this makes it much easier and much faster to parse the file and reconstruct the intended representation in whatever language or whatever tool you're sharing the data with. So as McKinney says on the original blog post, it's really about the metadata, maintaining the data about the data. So I guess we talked about CSV files, and not to hit on pandas too much, but this is just a sign of how tough it is to parse CSV files. I think there's probably about 50 different options here. I think when I first started dealing with data in Python, I used to just do 4-line in file, split on comma. That worked when I was writing the CSV file, but it definitely did not work when other people gave me the CSV file. So I think, as anybody knows, Mac and Windows have different ideas about how lines should end, and it's a lot of trouble. And reading and writing data should be the most boring and simple thing in your workflow. You just want to get it into your tool of choice and start doing work. And that is one of the reasons that Read CSV in Pandas has so many options and so many default values. You just want to point it at a file and get a data frame back and nothing else. You don't want to figure out, do I need to deal with different encodings? Is this UTF-8? Is it ASCII? Is this some sort of compressed file? Are the lines, do the lines have a carriage return, or do they have a new line character? So they did do a very good job of just making this work. 95% of the time you get a data frame back, which is great. But we could be better. So I guess a long digression to understand a little bit about why Feather and Avro and Parquet and all of these not CSV file formats are a little bit better. We need to step back and talk about computers. So it all starts with sand, and somehow we get from there to computers, but we'll skip a few steps. In writing software, we spend a lot of time trying to abstract things away. So we like to think that memory in a computer is just one big hash table and we can read any value arbitrarily. That probably was true like 20 or 30 years ago. It is definitely not anymore because we've had decades of growth at different rates in the speed of CPUs versus the speed of main memory and disk access. So memory speeds have grown at a rate much, much slower than CPUs. We think it's a big hash table. You can access memory anytime you want, wherever you want, all constant time. In reality, we have this really complicated hierarchy of caches and buses, and some are shared between cores, some are shared across all cores, some are unique to a single core. So really keeping the CPU occupied doing your data analysis doesn't really require understanding these at a fundamental level, but it requires knowing that there is something there, or that it is not as simple as the previous slide implied. This is my colleagues call this Bill's greatest hits. I post this on our hip chat room all the time. This is really from Jeff Dean, entitled "Numbers Every Engineer Should Know." These are relative latency numbers going from reading something from L1 cache all the way through sending a packet across the world and back. So really, we want to be in the good place at the very top. We want to be reading stuff out of the cache. We don't want to have cache misses and things like that. So the way this really works is when you go to fetch a value from main memory, rather than grabbing just that value, the CPU grabs an entire cache line. And I think on modern Intel CPUs, that's something like 64 kilobytes or I don't know, some big number. I'm not entirely sure what it is. But so for example, if you wanted like this yellow, my mouse does show it there. If you wanted this yellow value, it's going to load the whole thing in. And if you next want the blue value, well, hey, great. Blue value is already in the cache. So you don't have to go back through main memory. And the CPU sits idle while that's happening. So what's the implication of this for like data analysis and reading and parsing data? So it really means that the data layout on memory and on disk needs to be tailored for how you are actually going to access it. And I'm sure this is probably obvious to everybody here. That's why there's also the Fortran people and the C people have a completely different idea about how matrices and arrays are laid out in memory. So to really keep your CPU occupied while you're doing data analysis, memory needs to be, memory access depends on locality and predictability. So it's really about sequential access, reading things in order from left to right or right to left or whatever, just making sure that it's predictable and ordered will ensure that you'll have a good time and keep the CPU occupied. So that brings us to Feather, which is, again, loosely based on the Arrow file format. And the idea here is that obviously the on-disk representation of tabular data should look just like the thing that's going to be in memory when it's all read. So we really want zero parsing. We want to just move the data from disk to memory without doing any extra work of translation. And the other insight that I think Redshift is based on this, Parquet, a lot of more modern analytics tools are based on the idea that our workflows are generally based on columns. So think about taking the mean of some value in a SQL database or something like that. We generally do stuff on columns rather than on rows. So organizing, in that case, the Fortran layout, organizing the data in memory by column makes more sense than organizing it by row. So what that looks like is this. So this is actually from the Arrow website. At the top is the data as you would think of it. It's a table. In this particular example, it's session ID, timestamp, and then source IP. So imagine like some access logs or counter or something like that. So on the left-hand side here, this is ordered by row instead of ordered by column. The right-hand side is ordered by column. So all the values for the session ID are first, followed by all the values for timestamp, followed by all the values for source IP. So imagine you're trying to answer the question, like a distinct count on source IPs. On the left-hand side, you're randomly skipping over fields to read each of the red rows. On the right-hand side, you just find the offset at the start and you read all the way through to the end. So that's sequential access. CPU is reading from the cache most of the time instead of consistently or constantly invalidating the cache and swapping from memory. So again, this brings us to simplicity. We don't have to do any parsing because the Feather file format maintains the types. So reading is about the most uninteresting thing possible. There are no options other than overriding column names. You just give it a path and you get a pandas data frame back. So the exact opposite of pandas. I mean, pandas has sensible defaults. It's very rare that people actually have to mess with these, but they are there. So this is what the actual representation looks like on disk. It starts with a magic number and ends with a magic number. And then each column is serialized as an array with some more metadata. There's a bit mask at the very top that maintains the list of NAs. So dealing with float values, there is a special NA type, but there is no NA type for strings. There's no real obvious NA type for integers and other data types. So they kind of sidestep that problem and just essentially maintain a list, a bit mask of the things that are null and the things that are not, followed by the actual values themselves. So if If these are just simple types with fixed size, it will be the representation on the top. So think like an array of floating point values. If it's a variable size array, so like an array of strings, it will be the bottom one. Again, null bit mask, and then value offsets, recording where the start is of each value in the array. So this is, I guess I didn't draw the, imagine this is turned 90 degrees. Looks roughly like data frames in R. The pandas one is a little more complicated, but the idea is still pretty much the same. The actual data structure is a list of columns, and each column is a pointer to an array of the actual values. So we'll do some live code, and we'll see what Feather actually looks like. And so everybody look away for a second. I'm going to do something in R. So we just loaded the iris data set. I'm sorry I don't have anything more interesting, but this is available everywhere, and everybody should have it memorized by now. So we're just going to write this to a Feather file. Let's see. We will call it iris from R. Sorry, I can't spell today either. And then we'll quickly quit out of R, so hopefully nobody saw that. And we'll go back to Python. So I guess we can skip the stuff at the top for now. Loading that data into Python is essentially just import the Feather package. And then we read it with read Feather. And now we have a nice pandas data frame. That's the... Oh, sure. How's that? That's pretty good. Oh, sorry? Oh, thanks. So that hopefully looks exactly like the R representation. So we have some... I have no idea what these things actually represent, some sort of flower. And then the species column. So all the stuff that's supposed to be there is hopefully there. Notice we didn't specify any options to read data frame. It just turned out the way it was, or turned out the way it should be. So now I guess we'll read this in hard mode. We'll actually deconstruct and read it manually. So as I mentioned earlier, the Feather file format stores the metadata about the columns at the very end of the file, and they do this using flat buffers. Are there any Google people here? Okay, so flat buffers is a Google project. Python support is not actually all that great. It works sort of like protocol buffers and the similar tools in that you write a specification that kind of looks like C structs. This is what it looks like. And then it will generate code for you to read and write the metadata. So I think this was just an arbitrary choice by the Feather authors. JSON probably would have accomplished the same thing, but in this case, they get some sort of typed representation of the metadata. So behind the scenes, I generated the metadata, the flat buffers bindings for the Feather metadata, and here we're just reading it in. So we're just going to load that entire Feather file into just a byte array in Python. So that's just what we did at the top. We're going to unpack the metadata. So at the very end of the file, they store the metadata size. So we're just going to look up that, and that'll tell us how far to back up from the beginning of the file to the start of the metadata. And then we'll read the metadata here using this crazy weird command that I had to actually look up. It's not the most well-documented thing. And then we'll just print out the columns that are in the Feather file. So we can see sepal length, sepal width, petal length, petal width, and species. And then these are the offsets where each of the values actually start. So we can take a quick peek at that. So this one is 1208, so I have to remember that. So this is just a hex dump of the Feather file that I just wrote. We said that column was 1208, is that right? Yeah, so right here we have the, let's see, 3.5, and that should be width 3.5. Okay, so yeah, this is what it looks like on actually on disk. Again, we start with the magic number, end with the magic number. We have the metadata size here, and then actual metadata here, and then a bunch of columns in between. And then back to Python. So I guess just for fun, we can read one of these files into a NumPy, or one of these arrays into an actual NumPy array. So we'll do the easy one, which is just a string, or I'm sorry, just a floating point value, or an array of floating point values. So we grab the column metadata, find the location data, and then just read from the file from that offset plus the total bytes, and we end up with a NumPy array. So this should be the sepal length, which is this one, so 5.1, 4.9. So yeah, looks about right, hopefully. And then some of the harder ones, reading the string column names is a little bit trickier. These are encoded, these are done in two places. The list of the categories or the list of the strings is maintained somewhere else. And then what's stored in the actual array of values are just integers pointing to the label array. So this one is actually a lot trickier to parse, since the values themselves are integers and the actual string values are stored elsewhere. Pulling apart the pieces is not super obvious. So we can, oops. Can actually take a peek. So these are the species, which are, there are 3 of them, I believe, and they're just numbered 0 through 2. And then if we really wanted to, we could convert those to strings by looking up the value array at the end of the file. So they record it, they just concatenate them all together. So this is all of them squeezed together without spaces. And then we could convert that to a NumPy array and stitch them together and recover the actual categorical representation. So that's it for the live code. And so what are some other potential uses for Feather? To date, they've only finished like reading and writing, and they're really in like the proof of concept stage. Beyond that, so these are like some things that I would personally like to see. Oh, sorry, this should be full screen. In-place operations, so a lot of the things you do on pandas arrays, it would be pretty great if you could just memory map the Feather file and be done. No parsing, no moving, no copying. You want to do some sort of select based on rows or columns. It would be pretty great if you just didn't have to actually read the file, the Feather file, it just happened. What happens right now is, since Python and R have very different ideas about exactly how data frames are represented, the data are actually copied from the Feather format into the native representation of a data frame in R or a data frame in Python. The other, I guess, another nice thing about being able to share, or in-place operations, is that you would be able to share some of the operational code between languages. So instead of having pandas and having R, you would have a C++ library or a C library that just knew how to do all of the common data frame operations, and semantically it would be equivalent in the 2 languages. So that would just, it would make it much easier to collaborate. And I guess I covered 0 parsing, copying, and also as like a de facto interchange format. So as input to tools like scikit-learn or stats models, which already do a pretty good job of dealing with pandas data frames, scikit-learn in the background just kind of converts them to NumPy arrays, and I'm pretty sure it's the same with stats models. I don't see Skipper in here to disagree with me, but I'm going to assume that's the case. It would be great if we could pass. R does a very good job of dealing with things like categorical features and things like that. Scikit-learn, that's to some extent up to you, the user, to do that expansion. But it would be pretty nice if we could pass an entire data frame to scikit-learn with the types included, and just get that have that done automatically for us, like some parts of R do. And then also as output from tools like Postgres. So I think the Spark and Hadoop people are doing this with things like Avro and Parquet, and that the data storage tools are outputting these formats that are recognized and usable across different languages. So there is little parsing when you're moving from where the data are stored to where the data are used, and then through your analysis pipeline. So that's mostly it. I'll turn it over to questions. And I guess I would also like to reverse it a little bit and hear from you folks what keeps you using CSV files and what would make you switch to something like Feather and not CSV files. Yeah, with that, questions and comments? Yeah, that is actually stored in the metadata. The only encoding they have right now for string values is just UTF-8. There's nothing else. It's just UTF-8.
And is it like on a list of potential future features to be able to change that, or like you can write files?
That's a good question. I actually don't know. I'd imagine they would probably just stick to the one data format to rule them all, but it's certainly not out of the realm of possibility. I think they do have an option just to store raw bytes, so that would certainly be an option to sidestep like a particular format that's not supported. Sure.
Is there any support for concatenating or basically adding more data after?
There is not. Oh, sorry. Is there any support for concatenating Feather files, correct? No, not yet. I think that would probably require a decent amount of work just because of the way the metadata are constructed and the way the file is structured. I think you would have to rewrite the entire file to concatenate two files. So it's probably not like an in-place or a simple operation. It would definitely require like some processing and copying of all the data, and is not quite as efficient as just concatenating two CSV files, unfortunately. Sure.
How does it handle like escapable characters, and if there are, say, commas within the file that should be included in the cell?
So the question is, how does it handle escapable characters and things that it should be included in the cell? So it's not like a delimited format, so it's not putting commas in between string values. It's all the column types are typed, so it knows that this thing is an array of floating point values. This other thing is an array of strings, and it stores for the strings, since they don't have a fixed length. It stores the start of each string in the array. So if it has what would normally be a delimiter, like a comma or something like that, in the middle of the string, it doesn't matter. It's just part of the string value that it happened to save. Anything else? Sure.
How different is the Feather format from the in-memory representation in Pandas and R?
So how different is the Feather format from the in-memory representation of Pandas and R? It's pretty similar to R, minus the metadata part. R is essentially just a list of pointers, or an array of pointers to arrays of floating point numbers or integers or strings. The Pandas one is a little more complicated because they have a block manager that jams columns together of the same type. I think there's been some discussion about changing this lately, but it's actually closer to R than it is to Pandas. So I'm sure that's something that they'll eventually converge on, and maybe with Pandas 2.0 or Pandas 1.0, I guess. Anything else? Sure.
Will Spark data frame into Feather and also make next Spark data frame as a Feather?
So the question is, does it support sparse data frames? Not yet, to my knowledge. I think that's still very much a work in progress. I'm sorry?
Is it on the radar?
Oh yeah, it's definitely on the radar. There's been a few issues that people have filed about supporting sparse data frames. Yep.
Back to answer the question of why we still use CSVs after seeing this. So I work in data repository, and I'm very interested in the end-of-life process of data set. So for me, plain text, digital preservation, and access to
Actually, that is a very good point. And they do actually have big, oh, sorry. The comment was CSV files are a great long-term archival format because they require little knowledge and you don't rely on tools being available to read them because they're just plain text. Is that fair characterization? And I absolutely agree with that. And they actually have big, bold letters on the GitHub repository saying not to use this as an archival format. Again, because you can't just call less on it and see what's going on. That's definitely a drawback. But I think, at least in my work, I tend to spend a lot of time taking data from like a CSV file or from some database and turning it into a CSV file, and then doing something with it in R, returning another CSV file, and then doing something with that in Python. And a CSV becomes our way of exchanging data between steps in a long data processing pipeline. And I think that's where Feather could really shine. Anything else? Okay, great, thanks.